Hi, my name is Hidayah and my group mates are Nabil, Hadi, Faris and Sharina. In this video, we will be presenting our reports on two reports, which is Experiment 5 and Experiment 6. The Experiment 5's title is Gas Chromatography and the Experiment 6 title is High Performance Liquid Chromatography.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Nur Faris and I will present about the introduction. The title of the first experiment is gas chromatography. Gas chromatography is an analytical separation technique that analyzes compound eluted from the column, which carried through the column by a gas mobile phase. It is a stable, consistent technique for the separation of analytes from samples. However, it can take very long time to refine the separation of complex sample. Finite element method has been applied to estimate the retention times and peak width of analytes during liquid chromatography, two-phase partition chromatography and acoustic chromatography, but no gas chromatography has previously been conducted using this method. This video presents a theoretical model for estimating gas chromatography retention times and peak width. For each three chromatographic separation test analytes, the retention and peak dispersion parameters are calculated for 4 distinct column forms and 2 temperature gradients using the thermodynamic data derived from isothermal experiments for the chromatographic method. The prediction results are then compared to the experimental data collected under the same operating condition.
First, two sets of gas chromatographic experiments were performed using a 5890 series gas chromatograph equipped with a flame ionization detector, which is one isothermal and one temperature programmed. Secondly, the purpose of the isothermal experiments was to acquire data for calculating the thermodynamic parameters used to describe the temperature dependence of the analyte's retention. Thirdly, when these parameters had been determined, temperature-programmed chromatograms could be predicted using the method described in this paper. To evaluate the method, temperature-programmed experiments with the same running conditions as assumed in the computations were performed and the results were compared. Fifth, the isothermal experiments were performed at temperatures ranging from 40 to 120 degrees Celsius with 10 degrees Celsius increments, 2 runs at each temperature with all 4 columns, and thus 72 runs in total. Sixth, the mixture were also separated on each column using 2 different temperature programs. First, starting with a hold at 40 degrees Celsius for 3 minutes, followed by a gradient of either 4 or 8 degrees Celsius per minute up to 120 degrees Celsius. In each case, hydrogen was used as carrier gas and methane as hold-up time maker.
Moving on to result and analysis for experiment 5. As you can see, this is the graph for gas chromatography. Discussion. The best and poorest predicted chromatograms, which is 4 degrees Celsius per minute gradient with dB1 and 8 degrees Celsius per minute gradient with dB23 respectively, are graphically compared to their empirically obtained counterparts in figure 1. Generally, the predicted and experimental values shows an excellent agreement. With the 4 degrees Celsius per minute temperature gradient, the relative differences between the measured and calculated retention times range from negative 0.17 to 0.18%, corresponding to actual differences from negative 0.8 to 0.6 seconds. For the cases with an 8 degrees Celsius per minute gradient, the relative differences generally range from 0.10%, which is at 0.8 seconds, to 0.41%, which is at 2.3 seconds. except for the dodecane in the DB23 column, where the relative differences is 0.66%, which is at 2.1 seconds. The weak retention for dodecane in that column makes even small deviations relatively large. With the steeper gradient, the experimental values are always larger than predicted values, indicating that the temperature control of the oven may not be sufficiently accurate. Precaution and error. The fact that the predicted peaks in all cases are narrower is most likely due to the fact that extra column effects, both dispersion during injection and detection, were excluded from the calculations. To accurately predict a full chromatogram, such effects will have to be included. Another source of error in the peak width prediction is the uncertainty in the determination of the input parameters, especially the diffusion coefficients in the stationary phase. A detailed study on the errors on the calculated peak width caused by the deviations in the diffusion coefficients will be the topic of a future paper.
In conclusion, we have shown that the finite element method can be used to obtain accurate predictions of gas chromatographic retention. Even in the least good case, it was difficult to visually determine between the plotted predicted peak triplets and the measured chromatograms. Since the ideal peak widths may be determined, studies of residual peak widths, i.e. deviation between calculated and empirically determined peak widths, may give important clues regarding non-ideal behavior and extra column effects. The equation that was solved in this paper could easily be expanded to include inter alia, terms describing absorption, providing opportunities to make predictions for overloaded systems and systems yielding non-Gaussian peak shapes. Other possibilities include using the method to predict the behavior of analytes in pressured program gas chromatography and inverse chromatography. The references that we use are all gathered from scientific databases, and we have 4 references.
Second experiment is high performance liquid chromatography. Liquid chromatography is a method of separation analysis using the mobile phase of liquid and the stationary phase of liquid. Difference of analyte's polarity are the basis for the separation. The analyte that interact most in the stationary phase will elute later than the analyte that interact least in the stationary phase. Reverse phase chromatography is used in which the stationary phase is non-polar mixture, while the mobile phase is polar mixture. The variations in the polarity of the mobile phase will affect the interaction of the analyte with the stationary phase, and will also impact the separation efficiency. Change in the composition of the mobile phase can be done either by isocratic illusion when the composition of the mobile phase is unchanged during the analysis, or by gradient illusion, in which the composition of the mobile phase changes during separation, either constantly or step by step, in order to distinguish the broad spectrum of polarity of the analytes.
HPLC, liquid energy drinks were analyzed directly after ultrasonic gassing for 10 minutes. Energy drinks and vitamin supplements in tablets were weighted, dissolved in 150 ml of demineralized water and sonicated for 10 minutes. Secondly, the sample was transferred to a 200 ml volumetric flask and filled up with water to the mark. Thirdly, samples were protected from light by aluminum foil and analyzed using HPLC. HPLC analysis, the samples were centrifuged for 5 minutes at 14,000 grams. No supernatant for the tested products were observed. Thus, the recovery studies were not necessary. For each type of product, 3 independent samples were prepared. 6. Validation of the HPLC method included linearity, sensitivity, accuracy, and instrument precision. 7th, quantification of caffeine and vitamins was performed using an external standard method. At least 7-point calibration curves N3 were prepared with the aqueous solutions of standards at the levels covering those in the assessed samples.
So I'll be explaining the analysis of high-performance liquid chromatography, which includes the results and also the discussion. As you can see in this table, it shows the retention time and also the peak area of the energy drink and the caffeine and the water-soluble vitamins. Example of the water-soluble vitamins that are used in this experiment are ascorbic acid, folic acid, FMN, nicotinic acid, and thiamine. As you can see, this is a graph of the HPLC separation of caffeine and water-soluble vitamins that was monitored at 254 and 202 nanometer and using a fluorescence detector. Number 1 is the ascorbic acid, as you can see in the graph. Number 2 is nicotinic acid. Number 3 is nicotinamide. Number 4 is pantotenic acid. Number 5 is pyridoxal. Number 6 is pyridoxamine. Number 7 is pyridoxine. Number 8 is thiamine. Number 9 is riboflavin, 5-phosphate, and next is FMN. Number 10 is caffeine. Number 11 is folic acid. Number 12 is cyanocobalamin, and the last one is riboflavin. Based on the research that have been done, several types of compounds were used to observe their retention time and the peak area in an energy drink. The compounds that were used are caffeine and water-soluble vitamins that are listed in Table 1. Firstly, ascorbic acid has a retention time of 1.59 minutes and the peak area is 245 nanometers. Secondly, the nicotinic acid's retention time is 2.20 minutes and the peak area is 260 nanometers. Thirdly, the nicotinamide's retention time is 4.25 and the peak area is 260 nanometers. Next, the retention time of pantotenic acid is 7.94 minutes and the peak area is 202 nanometers. The next vitamin is pyridoxal, which has a retention time of 9.85 minutes and the peak area of 219 nanometers. Moving on to the sixth vitamin is pyridoxamine, which has retention time of 11.23 minutes and a peak area of 290 minutes. Next is pyridoxine. The retention time of pyridoxine is 12.86 minutes and the peak area is 290 minutes. Other than that, thiamine was also used in observing its retention time and peak area, which brings a value of 15.69 minutes and 245 nanometers respectively. Next is FMN, which has the retention time of 16.30 minutes and the peak area of 450 nanometers. The next vitamin is folic acid, which has a retention time of 17.58 minutes and peak area of 280 nanometers. Next is cyanocobalamin. The retention time and peak area of cyanocobalamin are 18.43 minutes and 207 nanometers respectively. The last vitamin is riboflavin, which has a retention time of 20.90 minutes and peak area of 450 nanometers. On the other hand, caffeine has the retention time of 16.33 minutes and the peak area of 270 nanometers. From the results obtained, the order of sensitivity of HPLC is expressed as ascorbic acid, which is lesser than pyridoxine, which is lesser than nicotinic acid. However, nicotinic acid is equal to folic acid. Nicotinic acid and folic acid is lesser than caffeine, and also cyanocobalamin, which has a sensitivity that equals to caffeine. Both of the compounds sensitivity of HPLC is lesser than thiamine. Thiamine sensitivity is lesser than pyridoxamine, and pyridoxamine sensitivity is lesser than riboflavin. Riboflavin's sensitivity is lesser than pyridoxal, and pyridoxal has a sensitivity lower than nicotinamide and also cyanocobalamin, which has the same sensitivity and is also lesser than FMN. FMN is lesser than pantotenic acid, which shows that pantotenic acid has the highest sensitivity.
In conclusion, the retention time of a standard solution caffeine is around 16.33 minutes. Meanwhile, the caffeine peak in a soft drink sample is 270 nanometers. Using the response factor method, the amount of caffeine in a soft drink sample is between 90 to 100 milligrams. This is the reference that we use for experiment 6.